everyone. This is the lecture for section 6.3, inverse trigonometric functions. So, up to now, right, we've learned about sine and cosine and tangent, right, and then the three other ones, right, secant, cosecant, and cotangent, right? We've learned how to graph them. We've learned how to play around with them in terms of identities, right, at least a little bit. Now we got to get into the inverse trigonometric functions, okay? If you guys remember from like the first chapter, right? Things that in mathematics, things that have inverses are very nice, right? So it's nice to be able to define inverses if something has one, okay? So that's what we're going to do here. The three big ones that we're going to be covering here are sine inverse, cosine inverse, tangent inverse. And it's nothing different than what we've been covering it's nothing different than what we've been covering over the last couple of weeks, right? It's nothing different from what we covered in chapter 1, okay? I'm just going to be redoing it basically, right, with the three important trig functions, sine, cosine, tangent. That's it, okay? So first of all, I want to go ahead and recall a couple things, right? That two functions are inverses if and only if both of these things hold, right? If you grab f, that's a bit too thick. Let me tone it down a little bit. There you go. If you grab f of g of x, right? Suppose f and g are the inverse candidates, right? And if this is equal to, and I'm going to put the other one here at the same time, if, whoops, not 0, x. Haha. If both of these are equal to x, right, then you have inverses. Okay, this means that f and g are inverses. Okay, and actually let me change this. Kind of don't like what I put there. It's actually supposed to be two separate, right? So g composed f of x is equal to x. There we go. Okay, both of these have to be satisfied. Both of these. Okay. Now, for the purposes of this class, right, you only need one of them, right? So choose the one that's easiest for you. Hopefully you guys remember that from chapter 1. Okay, and so long as you show one of them, right, you have an inverse. You've proved that f is an inverse of g and g is an inverse of f, okay? The other thing that you guys should remember, right, is that the domains and the ranges switch, okay? So that the domain of f of x becomes the range of f inverse, right? And vice versa. Okay, so let me actually do it this way. Domain slash range. And then you get to sort of pick your own adventure, right? Range slash domain. Okay. This is basically saying that if you had the domain and range for f, right, and there existed an inverse, f inverse, right, then the things would swap. Okay. So real quick, let me go through some of the domains and ranges for what we've got, right? So you guys hopefully remember that the domain for sine and cosine, those were both negative infinity to infinity. We were able to plug in any angle we wanted, okay? For tangent, right, we said it was all real numbers, basically, right? All, ooh. And the way that we write that is this, all real numbers, right? There was exceptions though, right? And the exceptions were x cannot equal, let me write these out, pi over 2, 3 pi over 2, comma, dot, 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 right? And then we can go backwards. So negative pi over 2, comma, negative 3 pi over 2, dot, 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 right? So we were able to go in both directions, right? Okay. The ranges for all three of these, right? Negative 1 to 1, because that's what happened on the unit circle, right? Sine was the y portion of our coordinate, right? And on the unit circle, that went from negative 1 to positive 1. It didn't go outside of that, right? Same thing for cosine, so negative 1 to 1, okay? And then tangent was the squiggles, if you guys remember the squiggles, right? Negative infinity to infinity. It didn't matter which one, right? It didn't matter what y we wanted. There was an x value that hit it, right? Okay, so same thing still works here, okay? So that means that this one and this one, the domains are going to be from -1 to 1 for both sine inverse and cosine inverse, okay? And the ranges are going to be -infinity to infinity, okay? Same thing for tangent. Everything switches. So it's going to be, my range is going to be -infinity to infinity, okay? And my domain is going to be all real numbers, okay? Yeah, let me do real numbers. Real numbers, right? Except x cannot equal, right? -3 pi over 2, and then dot, dot, dot backwards, right? -pi over 2, pi over 2, dot, 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 dot. Okay? There we go. So everything sort of still worked out. Okay? It's not bad. It's not bad. Now, what I do want to sort of stress, and this is something that we're going to have to pick up now, right? Is this. So I'm going to go ahead and scroll down a little bit. Okay? What I want everybody to look at is this. Okay? That, and I'm going to write it in the hot pink here. Okay? When we were talking about these three, sine, cosine, and tangent, right? There was a meaning behind the sine of x, the cosine of x, and the tangent of x, right? When we were talking about sine, cosine, and tangents, the domain, the x values that were coming in, right? The x values that we were putting into these functions, right? These were angles. So when we were talking about sine, we were saying sine of a particular angle. We were saying sine of 90 degrees, cosine of 60 degrees, tangent of 45 degrees, right? And what was popping out, right, were essentially lengths, okay? That sine of 90 degrees was a particular length on the unit circle. Got it? Cosine of a particular angle was a particular length on the unit circle, in particular the x, right? And then tangent was going to be the ratio of the two, right? Okay, that was what happened with good old regular trig functions. We gave it angles, right? And it gave us lengths. Cool? Okay. Guess what happens guess what happens with inverse trig functions, right? Those are backwards. So for inverse trig, I'm going to put this, actually, I'm going to put this up here. So we gave, let me do it in a nice, now I'm trying to just find the right color. There we go. We gave angles to trig functions, right? And what popped out was lengths. Okay, now these are going to go backwards, right? So for inverse trig functions, we are going to give it lengths, right? We're going to give it lengths and it will pop out angles. Okay, essentially backwards from what the trig functions were doing. You guys see that? Okay, trig functions grabbed angles and gave us lengths, right? Inverse trig functions, we give it lengths and it will give us angles. Okay, so let's go ahead and start practicing a little bit. Okay, so we know this from our unit circle. Okay, go ahead, get your unit circle out. Sine of pi over 6, we go look at pi over 6. The sine of it is going to be 1/2. Okay, so then when we look at this, right, this is what should be going on in your head here, right? We are saying, right, sine of some angle theta has to be equal to 1/2. Okay, what would this angle be? Okay, and if you look, right, sine is equal to 1/2 at two different locations. One of them is pi over 6, and the other one, okay, is 5 pi over 6. Okay? Cosine of pi is equal to -1. We know that one, okay? But same thing like we did above here, right? This is saying I want the cosine of some angle theta to be equal to -1. Where should that angle be? That should be pi. In this case, there's only one. There's only one answer, okay? Now, remember what we said back when we were doing inverses back in chapter 1, okay? It has to be 1-to-1. So for every y value, there has to be only one x. There's a problem right here. Okay, turns out this one is not an answer. Only pi over 6 is. So, what the heck? Okay, so that's where we have to bring back our 1-to-1. All of them have to be 1-to-1. Now, we've seen what's going to happen here. We've seen what is going to happen here before, okay? There are certain functions where we have to basically, essentially, cut certain parts of our function out and make it 1-to-1, okay? And that's exactly what we have to do with sine, cosine, and tangent, okay? So for all three of these, we have to reduce their domain. We have to restrict the domain. Okay. So when we talk about this, when we talk about sine inverse of x, right, we know that the domain, this doesn't have to get changed, -1-1, okay? But we do have to restrict the range, okay? And that's going to be -pi over 2 to pi over 2. Okay, so we are only talking about my angles that pop out in this range right here. Okay, same thing happens with the rest. Okay, so then the domain is still going to be -1-to-1 for cosine inverse, right? But the range is now going to be 0 to pi. Okay, and then lastly, okay, the domain for tan inverse, -∞ to infinity, that's fine, but the range we have to cut down. -pi over 2 to pi over 2. We are done. Okay. Now, why does this work? Okay. Let me actually scroll to the side a little bit. Okay. And let me take a look at the unit circle that I have right here. I can never choose it. Nope. There we go. Okay. So watch this, yeah? Okay. For sine inverse, we are only looking at angles that show from -pi over 2 to pi over 2. That is this strip right here, from down here all the way up and around to back here, right? So now, look at this, right? Outside of that arc, outside of the right-hand side of our unit circle, right, our values for sine start to repeat. That made it 1-to-1. Can you guys see that? Okay. For cosine, same idea. We start here and we're going to go all the way around, all the way back to here. That is the range for cosine inverse, right? And if you take a look at it, right, all the angles past 180 degrees, or pi, right, just start to repeat for cosine outside of this blue arc. Okay? And then same thing for tangent, right? If you take a look at tangent, that's saying from -pi over 2 to pi over 2. Okay? Outside of this, your tangent values start to repeat again. Okay, that's the easy way to explain. That's actually the entire way to explain why we have to cut away the rest of the unit circle so that sine inverse, cosine inverse, tangent inverse become one-to-one. So we do have inverses. Okay? Okay. Now, hopefully that sort of makes sense. This is going to take a fair amount of practice. Okay? I'm going to go ahead and show you guys what sort of in practice this is going to look like. Okay? So suppose we wanted to find these angles, right? So this is asking for all of these. It's asking us to give us some angle theta, right? This is equivalent to saying, we've already done this one, right? This is equivalent to saying, I want some sine of some angle theta to be equal to 1/2. 1/2. Okay? As we saw above, right? The two answers that we get are these. Theta is equal to, actually, you know what? Yeah. Pi over 6, 5 pi over 6. Okay? Now, remember what I said, right? The range for sine inverse is just from negative pi over 2 to positive pi over 2. Okay? Let me actually bring this back over here. Let me grab my unit circle that I brought. Come on. There we go. I'm actually going to put it right here. Okay. So look at this, right? Pi over 6 is here. 5 pi over 6 is right here. But the answers for these have to exist in this little strip right here. Right? So and that means this one is a nope. So my answer's got to be pi over 6. This is my only answer. Got it? Okay, let's try it again. So when I write this, right, this is some angle theta. This is basically saying, right, cosine of some angle theta has to be equal to negative square root of 3 over 2. Okay, if we look at our unit circle, there are a handful of angles, 2 of them, where the cosine is negative root 3 over 2. This one, right, and this one. So my two answers here, theta, is going to be 5 pi over 6, 7 pi over 6. Okay, but cosine, the answers, the range for cosine inverse has to exist in this strip right here, right? So that automatically cancels out that one. Can't be this one. It can't be 7 pi over 6. My answer is the 5 pi over 6. We are done. Woo. Okay. We're getting, hopefully you guys are getting the hang of this. Let's move on to the other ones over here. Okay. Oh, let me do this. You guys see that it's, let's see, order. Bring to front. Bam, there we go. Cleaned up everything. All right. Doing this again, right? Theta. Sine of some angle theta has to be negative root 2 over 2. My angles, right, for this one, okay, is going to be, let's, negative root 2 over 2. So this one, so you guys see that? And then this one. Okay, so in these cases, right, I have 5 pi over 4 and 7 pi over 4. Okay, my answers for sine inverse have to land in here. Right, so automatically this one gets canceled away. It can't be 5 pi over 4. So it's not this one, right? Now, here's another thing, right? remember how I said the angles have to be, for sine inverse, the angles have to pop out somewhere between negative pi over 2 and pi over 2. This is not in there yet, right? But there is a coterminal angle in there that is equivalent to 7 pi over 4, right? So it's not this one either, but that is coterminal to negative pi over 4. There you go. I know you guys don't like coterminal stuff, but like I said, coterminal angles are here, so we don't have to use coterminal angles. Okay. Last one. Tangent inverse of 1, we say that that's equal to theta. So I need a tangent of some angle theta to be equal to 1. You guys remember that tangent is equal to sine of theta over cosine of theta, right? So then that means my sine and my cosine need to be exactly the same. There are two angles that do it, right? There's this one, and then there's this one. In this one, both are positive. In this one, both are negative. So then you get a positive 1, right? So my two answers here, theta has got to be either pi over 4 or 5 pi over 4. Again, tan inverse, the answers for tan inverse, the angles for tan inverse have got to, I wanted to keep those actually. The angles for tan inverse, look at me go, have to exist from negative pi over 2 to pi over 2. So guess what? Not that one. So I get to cancel out 5 pi over 4, and I get left with just pi over 4. This is the only answer we got. Okay. There you are. Okay. Practice these. Give me a practice. Yeah. We'll do these in class, obviously. I'll double check everybody's work and all that good stuff. Yeah. Okay. Using your calculator. Okay. So when this is more of how we would use inverse trig in the more applicable sense, in the practical sense. Okay. So for this, I want to open up Desmos. There we go. Okay. Let me open up my graphing calculator. Okay. I'm going to make it nice and big. And what I want to remind everybody is when you go up here to graph settings, right, you have two modes, radians and degrees. Depending on which one you're set to, right, that's the answer that's going to pop out. That's simple. Okay, so right now I've chosen radians, right? Okay, so now let me do that. Here we go. So then sine inverse of 0.97. Okay, so to get there, you guys remember this little keyboard at the bottom? Functions, inverse trig, they are separated away. So I can do inverse, sine inverse of 0.97. And there we go. So right now, it's giving me the answer in radians, right? So this is going to be 1.32523 radians. Okay, so this is basically the measures if you were to mess around with pies, right? Okay, now the other one. So if I click degrees, right, that is equal to 75.9301 degrees. So this would be more familiar for people, right? If you're trying to find the degrees of something to build, right? And then this other one would be if you're messing around mathematically doing stuff with radians. That's it. Cool? All right. Let's move on. Let's keep going. So now, how do we do this stuff? Okay. So let's say we want to find a missing angle. Let's say we want to find that angle theta, okay? But we're given two sides, okay? Usually, right, up to now, I've given you the angle and I've made you find one of the sides, right? But in this case, the angle is missing and I'm telling you, find my angle, right? So if you take a look at what we have, the same stuff, right? We still need SOHCAHTOA, right? We still need SOHCAHTOA. We have an angle, we have its adjacent, and we have its hypotenuse. This is textbook cosine, right? So cosine theta has to equal the adjacent, right? 9 over 12. 12. 12. Okay, I'm going to grab this and move it away from SOHCAHTOA just a little bit. Okay, now we know what cosine is, right? But we don't need the cosine. We need that angle, right? So what tends to happen is the thing. Just remember, right? If you guys remember, way back in the day, right? How do you get rid of an addition? You subtract. How do you get rid of a division? You multiply. How do you get rid of a square? You square root, right? This is working out the exact same way. So how do you get rid of a cosine? You do cosine inverse on both sides. Yeah. So then what happens here, this is sort of like the motions that you're supposed to have the cosine inverse and the cosine go away there, but you have to take the cosine inverse of the other side. So theta is equal to cosine inverse of 9 over 12. Okay, now, what are my two answers? Right? That's where Desmos comes in. So where's my browser? Okay. Now, if you want, you can type it in. I'm just going to go ahead and use the function. So cosine inverse of 9 divided by 12. 9 divided by 12. Okay. Now, keep in mind, right? There are two modes in this case, right? So there are two answers here. This one, if you guys look over here, this is set in degrees. So right now, this answer that's popping up, 41 point, uh-oh, I lost it. I lost it. 41.409. Let me do this. There we go. 0.409. This is degrees. EES. Okay. And if I click on radians, now it's giving me 0.72273 radians. Got it? Awesome. Okay. It's simpler than it looks, really. I got some quick checks here for everybody to try out. Not too bad, right? Okay, moving on. Okay, composites. Composites of trig and inverse trig stuff. Okay, the way that you work with these are from the inside out. Okay. Let me bring my unit circle. Please don't hate me. Come on. I like to think of myself as very technologically savvy, but sometimes there are things that I'm like, oh, come on. There we go. Okay. So there we go. I'm dragging around my unit circle. Okay. So now, there is a little bit of a problem that happens because of inverses and the definition, the overall general definition of an inverse. Okay. And this is the problem. Okay. You would think to yourself, just how I did up above, that, oh, nah, right? So my answer should be 5 pi over 4. Yay, we're done. No. So remember, sine inverse, the angles that pop out for sine inverse have to be somewhere from negative pi over 2 to positive pi over 2. It has to be in that right half of the unit circle, right? So what we have is this. Let's go ahead and work with this first, right? What's sine of 5 pi over 4? If we look at the unit circle, 5 pi over 4, sine of it is negative root 2 over 2. So then that means this reduces down to sine inverse of negative root 2 over 2. And what we were doing before is I can call this theta, right? And this is saying basically, right, sine of some theta has to be equal to negative root 2 over 2. Now, this is not entirely incorrect, right? Because if we look at our unit circle, when is sine equal to negative root 2 over 2? It's going to be here. Hopefully you guys see that. And here. At 5 pi over 4 and 7 pi over 4, or negative pi over 4, right? So then from here, we get this, right? 5 pi over 4. Oof, you need more space there. 5 pi over 4 and 7 pi over 4, right? Both of these can't be the answers because this one is clearly not in it, right? And this one isn't either, but it's coterminal, right? So we get theta is equal to negative pi over 4. So this answer, this thing right here, is actually equal to negative pi over 4. This is the actual answer. Okay, but it's because of our definitions of inverses. Okay, it is because of our definition of inverses that this is the case. It just doesn't happen to cancel out like you'd think it would. Okay, now this gave us a way to solve out all the stuff that we have to do with them, right? Okay, so let me go ahead and scroll down a little bit. I'm going to bring my unit circle with me. Okay. So, like I said, we work from the inside out, right? So, bam. So, tangent of pi over 6. This is equal to sine of pi over 6 divided by cosine of pi over 6. 1/2, whoa, divided by root 3 over 2. So this is going to be square root of 3 over 3 if you do your math right. So then now, tangent inverse of square root of 3 over 3. Okay, there are two angles that do it. I'm going to call this theta. So then this is saying I need a tangent of some theta is equal to not negative root 3 over 3, positive root 3 over 3, right? Theta has got to be two angles. Here are the two. That one and this one. Okay. Tan inverse has got to live in here. Yeah. So then that means this one can't be it. So I'm going to do that. I'm going to put down pi over 6, 7 pi. We can see that this one's not the case. So all that gets left is this one. We are done. These are nice and complicated. Just follow it along, okay? Okay, another one. Whoa. It's got sort of the same issue. So we work with the inside and go out. Okay, sine of pi over 6. We go over here to pi over 6. We need sine. That's going to be 1/2. right? And I want to call this theta. Okay, so this means sine sine of some angle theta is equal to 1/2. Okay, theta has got to be only two options. Okay, this one, pi over 6 and 5 pi over 6. Okay, sine inverse, let me actually write those down first of all. Pi over 6, 5 pi over 6. Sine inverse has got to live in between here and here. So automatically this one doesn't count. It's only this one. So it's not that one. It's got to be this one. Okay? Okay. Uh, okay. I've got a couple of these for everyone to try. Okay? Now, in the ones from before, the inverse function was outside, correct? Right? We can also have the inverse function inside. Now what? Okay. For all of these, SOHCAHTOA the heck out of it. Yeah? I'm going to show you how. Okay? Okay. So I'm still going to work from the inside out. So I'm going to grab this one. Okay. Notice how the cosine inverse is inside the trig, right? So the inverse side is in the inverse thing is inside, right? The trig thing is outside. Okay. Okay. I'm going to grab that thing. Okay. Cosine inverse of 4/5 is equal to some angle theta, right? Cosine of some angle theta has to be equal to 4/5, right? What I'm doing here is this. I made that theta, so what I'm looking for now is sine of my theta. What is this equal to, right? Okay? And we're going to use cosine to find it out. Okay? So, I'm going to make my triangle. All of these are going to require a right triangle of some sort, so here we go. Okay? I'm going to assign my angle theta. Okay? According to my work, cosine of that angle should be 4/5. So that means my adjacent and my hypotenuse are given to me. 4 and 5. Cool? Okay. So now that I have these two, I can find my missing length, right? So then this is going to be, I'm going to call it A. So A squared plus B squared is C squared. I can use Pythagorean theorem. This is a right triangle. Okay. A squared plus 4 squared is equal to 5 squared. A squared plus 16 is equal to 25. A squared is equal to 9. A is equal to 3. So and this makes this missing length 3. And that's it. Because now, you guys remember, I was trying to find sine of this triangle. The thing that was missing for sine was the opposite, wasn't it? And we just found it. So then that means sine of my angle, which is equal to the sine of my original thing, of cosine inverse of 4/5, that has got to be equal to 3/5. We are done. This is just getting you guys practice for using these things out. That's it. One more. Same idea, right? I'm going to grab the inside thing, separate it out. oh, not cosine, tangent inverse of 7 over 4. That's got to be equal to some angle theta, back from what we were doing before, right? Tangent of an angle theta has to be equal to 7 over 4. I make my right triangle. Okay, tangent, this thing right here, tangent, according to SOHCAHTOA, is opposite over adjacent. So that's theta. Opposite is 7. Adjacent is 4. So I need this, right? And we're looking for sine of my angle theta, whatever that is, right? So I need my opposite and my hypotenuse. I'm off to look for my hypotenuse now, right? 7 squared plus 4 squared is equal to c squared. I'm going to make that c. 49 plus 16 is equal to c squared. 65 is equal to c squared. C is equal to the square root of 65. Okay, so sine of theta, right, is equal to my opposite over hypotenuse, right, which now ends up being the sine of the tan inverse of 7 over 4. This has got to be equal to 7 over the square root of 65. Dunzos. Bam. Like I said, this is just practice for messing with sine, cosine, and tangent inverse in particular problems, right? Will you ever see something sort of as finicky as this? Probably not, okay? But it's providing you practice, okay? You will see something like this much later, much later, to a lesser extent, okay? Once you get to Calc 2 in particular, okay? All right. After that, lecture questions. Woo! If there's any questions with the stuff that I just covered, ask me during my quick check time or come by my office hours, okay? Besides that, happy studying.